There are two types of rate laws in the world. There are differential rate laws. That's the one we just wrote. A differential rate law is how rate depends on concentration. So when we wrote rate is equal to K, yeah, that's it. Differential rate law. If I say rate law, this is the one we're talking about. There's also one based on calculus. The integrated rate law talks about how the concentration is affected over time. Instead of saying, well, the reaction started out with this rate, the integrated rate law lets us say, after 15 minutes, how much reactant was used up, or after 15 minutes, how much product got made. It lets us track the concentration versus time. Don't be afraid that it involves calculus. You don't have to know calculus. It's just if you understand calculus, it'll make it easier. I want you to get out the equation sheet I gave you, find the part on kinetics, and find something that looks like this equation right here. It won't look exactly like it, but it'll look similar. Did you find it? Good. I'll throw my copy of it up here on the screen. Now look at the one up here and look at the one down below. What's the only difference? I've rearranged mine so that it's in slope-intercept formula. So what kind of graph would I have to draw in order to get a straight line out of this? Well, my y-axis is over here, the natural log of the concentration of the reactant at time t. What's my y-intercept? That one's down here. That's the natural log of the concentration of that reactant at time 0. In other words, the initial concentration. What would my x-axis be? That would be the t part, time. And how would I know what the rate constant is from the rate law? It's the slope of the line. So the slope of the line should be negative k. So we can use this in class to find out all kinds of things. Since we're using up reactant and it's going away with time, we can also invoke something called half-life. Now for a first order reaction, this is one in which the exponent was 1. All you need to know is that there is a half-life equation, and this half-life equation is on the equation sheet. But the most important thing to know is the half-life does not change. So if you started out with 10 moles of it in a liter and half of it went away after 5 seconds, then you could say, oh, I know that the next half of it is going to disappear after another 5 seconds. So the half-life does not change. Very, very important. We also have a second order integrated rate law. Look on your equation sheet again. You will notice that this is the second equation on the sheet. That's how you know which one's first and which one's second. Notice that it's different from before, that I have rearranged mine to look like slope-intercept formula. You need to be able to do that. But instead of the natural log of something, it's 1 over the concentration of something. So my y-axis is going to be 1 over the concentration of the reactant, and my y-intercept is going to be 1 over the concentration at time 0, or the initial concentration. I can still find the rate constant because it's going to be the slope of the line. In a second order reaction, the half-life changes. So it won't always be 5 seconds. It won't always be 7 seconds. It won't always be 2.5 hours. It will change as time goes on. So we've talked about first order. We've talked about second order. What do you think is next? One of you out there said third. Nope, it's 0. A 0th order reaction, it doesn't matter what you do to the concentration. It's an exponent of 0. And anything to the 0th power is 1. So it has no effect. It's like multiplying it by 1. There is an integrated rate law for a 0th order, but it's not on your equation sheet. You don't need to worry about it. The half-life, you also don't need to worry about this equation. We can summarize them all looking at table 12.6. kind of lays them all out. So that's not a bad thing to look at in your book.